Perfect. So let's begin with a quick review of single electron atoms. And for that, let me start. Sharing my screen. Okay, so I'll be taking these lectures on this OneNote for Windows. And at the end of each lecture, I will be uploading their PDF version to LMS. So even if you don't want to take any notes during the class, you will have access to these notes at the end of the class. Okay, so let me start with a review. So this week we will be reviewing single electron atom. And for that, let me start with the a topic which is even simpler than that, which is two non-interacting particles. So I know that in an atom, for example, hydrogen atom, we have two interacting particles, but let's go even a step back and say we have two particles. Let's say particle of mass m1 and some particle of mass m2, and this one is located at R1, and this one, let's say, is located at some position R2. And let's see if we want to treat them together quantum mechanically, how we can do that, and what are the consequences of their non-interaction. And then we will go on towards understanding interacting particles. And from these two non-interacting particles, we will be able to generalize to many non-interacting particles as well. So since this particle and this particle, they are both non-interacting, and let's say its position always is given by some coordinates R1, where R1 essentially is x1, y1, z1, and R2 is specified by x2, y2, z2. They are 3D coordinates. And suppose there is some potential which acts on this one and that one independently. So in total, let's say the total Hamiltonian that is acting on this system is given by the Hamiltonian for particle 1 and Hamiltonian of particle 2. And we can write the total Hamiltonian as some of these Hamiltonians, because we can just add their total energies, where just to be more specific, H1 is a function of R1 only, and H2 is a function of R2 only. Since there is no interaction, there is no term that depends on R1 and R2. So if we have a Hamiltonian like this, which can be broken down into two terms, and both depending on different coordinates, we can write the time independent Schrodinger equation for them like this, and we can simplify it considerably. For example, this H can be written as H1 plus H2, and this psi is the total wave function of the two particles. And since we have two terms that are independent of each other, we can start by trying a solution psi, which is, let's say, product of two terms. One term depends on R1 only, and another term depends on R2 only. This is called separation of variable. And hopefully you would have studied the separation of variable technique already in some quantum mechanics course. So if I, break this psi as a product of two terms, and then I substitute this psi here, and then I can see that this H1, when this will operate on this thing, so H1 psi 1 function of R1 only, psi2 function of R2 only, and then H2 operating on psi1 and psi2 equal to E psi1 psi2. But since this H1 is function of R1 only, it only acts on this one, and this psi2 can come out. So I can write it as psi2 H1 psi1. Similarly, this is function of R2 only, so this doesn't do anything to psi1, so psi1 gets out, and H2 psi2 E psi1 psi2. Let's divide by psi1 psi2 on both sides. So we get when I divide by psi1 psi2, this psi2 cancels out, so psi1 and then H2 psi2 psi2 is equal to E. Now you see, this is something that is only function of R1, and this is something that is only function of R2, but this is a constant. This is the total energy of the system. So it means if this, which is a function of R1, and if this, which is function of R2, has to add to give a constant, there is only one possibility, and that is that this has to be a constant and this has to be a constant. Because if this is, function of R2, it cannot be cancelled by anything in this one. And if there is any term depending on R1 here, this cannot be cancelled by this one. And to satisfy this equation, there's only one possibility, that this is equal to some constant, let's call it E1. And this is equal to some constant, let's call it E2. And you will soon see why I have symbol E for these constants instead of just C1, C2. And this is equal to E. So there's this constant, we'll give it some physical significance a little bit later, and this is constant, but we do know that they should have dimension of energy because they're both adding up to give us total energy of the system. So it means that if this is equal to E1, I can write H1 psi1 psi1 E1. So the other term is equal to H2 psi2 psi2 E2. So this is H1 psi1 E1 psi1 H2 psi2 E2 psi2. But this is nothing but the Schrodinger equation if only particle 1 would have present in the system, with E1 the energy of the particle. And this is nothing but the Schrodinger equation if there would have been only one particle, particle 2, present in the system, with E2 as the energy of the system. It means if we have two non-interacting particles, their total energy is nothing but their energies as if they are only present by themselves and nothing else is present in the universe. So, and their energies can be easily found by just solving for their individual Hamiltonians and not worrying about the Hamiltonian for the other particles. So, and their total wave function of the system is nothing but the product of the individual wave functions of the systems. So this actually gives us a nice way if we have, let's say n non-interacting particles. We can easily find the total energy E as just sum of individual energies, and the wave function is just the product of individual wave function. And to find these energies, we just have to solve the individual Schrodinger equation for each of the particle without worrying about the rest of the particles. So this whenever we have non-interacting particles, we can quickly just solve for individual particles and then add up their energies. And that's how we can quickly find the solutions and energies for non-interacting particles. If the universe would only be composed of non-interacting particles, life would have been pretty easy. But perhaps life would only have been meaningful for individual particles only, because we wouldn't be able to get a lump of particles. Anyway, so this treatment can be extended to even a single particle. Suppose you have a 3D rectangular box and you have some particle in there. Or you have, a harmonic oscillator, which is 3D. So this is 3D box. But let's say you have, so this has a potential, something like this, that this is non-zero when your x is between, let's say, 0 to a, your y is between 0 to b, your z is between 0 to c, and it's 0 otherwise. So it's something like this. So let's say we have a 3D harmonic oscillator. So it has a potential profile like this, that let's say half kx square, half kyy square, half kzz square. Or we have maybe we have a free particle. So a free particle is, for this v is 0. So for these situations, you see the Hamiltonian for the single particle is something like this, that we have px square, py square, pz square. So for 3D box, we have, this constant term, and I can add this constant to, any of it. Or for the harmonic oscillator, for the 3D harmonic oscillator, we can have h like this, px square 2m plus half kx square, py square 2m plus half kyy square plus pz square 2m plus half kz square. So here we have a situation, even for if we have a free particle, there would only be term like these momentum terms or no potential term. But in all of these cases, I could write my Hamiltonian as Hamiltonian of x component depending only on the x variable, and Hamiltonian term of y component, and a Hamiltonian term that only depends on z component. So this is actually exactly the similar situation as we were talking about in non-interacting particles, because again we have Hamiltonians terms that are independent of each other. So this doesn't depend on any of that. This doesn't depend on any of that. So we can actually show in using exactly the same argument that for this one, all we have to do is find energy corresponding to this term, and this term. For example, we solve a psi x and find some ex, and we solve for the y component of the Hamiltonian and find energy corresponding to the y component, and we solve for the Hamiltonian for the z component. So the total wave function xyz is just some constant time psi x, psi y, psi z, and the total energy is just the sum of three energies. So this independence, either in terms of non-interacting particle or for the same particle in terms of different degrees of freedom. If we have a Hamiltonian that have terms that are independent of each other, we can do exactly the same invocation and get this result, that we just have to solve for each terms individually and then add the energies for each term, and to get the wave function we just multiply the wave function for each individual degree of freedom, and we get the total wave function. Okay, so these, this initial review that I'm doing is because this is going to be very useful for us. We will be studying particles in 3D space, and sometime if we are able to, separate our Hamiltonian into terms that are independent of each other, then we don't have to worry about the total Hamiltonian at the same time. We can just worry about individual terms at one time, because that will make our life very easy. And similarly, whenever we have multi-particle, even if we can, separate interaction between some particles, then we can break up of our problem into, component problems and then solve smaller problems instead of solving a bigger problems at the same time. So this simple result is going to be, very helpful for us when we will be solving for many body quantum physics. So any questions so far? Please stop me anytime if you find anything confusing. By the way, this is chapter 5 of our textbook. So you can also see the review there. I'm doing it a bit in condensed form, and he has done it in an even detailed manner than I'm doing it here. Okay, so after discussing the non-interacting particles or independent degrees of freedom, let's now start working for interacting particles. So let's start with 2.
सर ये जो आपने मेन बुक बताई है उसी का चैप्टर 5 है जो पहले नंबर पे लिखी हुई
जी जी, वो मैंने LMS पे अपलोड भी की हुई है उसकी PDF से.
थैंक यू सर.
Okay, two interacting particles. Okay, so before I actually do their quantum mechanical treatment, let me do their classical treatment, because that will be helpful for quantum mechanical treatment. Okay, so some of you are writing in the chat. Somebody said that they don't have access to LMS. Hafsa, are you registered for the course? Okay, so if any one of you doesn't have access to LMS, I think they should have it soon, but you can send me an email and I will add you to the LMS. Just a comment about chat. Unfortunately, the way the system is set up in front of me, I am unable to monitor the chat during the lecture. So please, if you have any question that you want to ask, just unmute and ask the question. But of course, you can post the question in the chat for your classmates to answer. They can help you out if you have any question. Maybe you just post it there, and other people are welcome to answer that question during the chat. And if it's not resolvable or if there's an issue, you can always talk to me. Okay. All right. So let's start with two interacting particles now. So suppose I have one particle here and one particle here, and suppose this is M1 and M2. And in this course, and actually in most of physics, we are usually concerned with the central forces. So that's what I'm going to assume in this in these interacting particles as well. So central forces are forces of this type. For example, you have two particles. So a central force is that if there is an interaction between them, the direction of the interaction, either it is repulsive or attractive, it's it passes through these centers of these two particles. So this is the type of interaction that we would be interested in. It's not like, okay, this particle is putting a force on this, which is directed along this line or along this line or this line. That is not allowed. That's not central attraction, that central interaction that we will talk about in this course. So all of our interactions would be central between the two particles. That is, they are directed along a line which passes through the center of these two particles. And if we work out the potential for these central interactions, we see that the potential is then only function of the distance between the two particles, and it's independent of their individual location. It doesn't matter if your particles are here or if your particles are here, as long as the distance between these particles is the same, the strength of interaction and the direction of interaction is the same. So the potential is function of the distance between the two particles only. That's a characteristic of the central force. So that's the type of interaction that we are interested in right now. That the force, the potential is function of the distance between the two particles only, which means that if we take this particle to be located at R1 and this particle to be located at R2, we will be working with another variable, which is the distance vector, displacement vector between these two particles, and let's call it some R vector. And by convention, we will always be taking it, for pointing it, from particle 1 to particle 2. And then most of the time, we will be working in the center of mass coordinate system. So let's say this is the center of mass of this two particle system. And suppose the position vector of the center of mass of these two particles is R. So this, this position of center of mass can easily be computed. Because this is nothing but a weighted average of these position vectors by their masses. So this R vector is nothing m1 R1 plus m2 R2 by m1 plus m2. For example, if both of the masses are equal, then this point would be lying right in the middle. So then this would be just R1 plus R2 by 2. But if this is a more massive particle than this one, so then the center of mass would be closer to this. So this will have a higher weight than the other one. And in the special case where you take this m1 to go to infinity, for example, you consider this m1 to be the nucleus and m2 to be the electron. And if you assume that the nucleus is infinitely heavier than the electron, that m1 is infinity, then if this is infinity, there's infinity here, this m1 can cancel out, and this R will just be R1. And some of the time we would be doing that as well, that we will be taking our center of mass to be located at the center of the nucleus. But in general, we can see that the center of mass would be somewhere between the two particles. So this is the center of mass coordinate. Similarly, this small R vector is nothing but R2 minus R1, which means that if we have this x coordinate representing R, so this is x, y, z. So x is nothing but x2 minus x1, y is nothing but y2 minus y1, and z is nothing but z2 minus z1. Now, we can express these R1 and R2 in terms of this capital R and small r, because these are two equations, and I can solve them simultaneously for R1 and R2 using the techniques of simultaneous equation. Then you can see that R1 comes out to be R minus M2, M1 plus M2 R, and R2 comes out to be R plus. I leave it to you to show that this is indeed the case. So we can use actually then these equations to convert from the absolute position to center of mass and relative position. This is the relative position vector of particles, and this is the position vector of the center of mass. Since the Hamiltonian operators invariably involves the sum of kinetic and potential energies, we for potential, I have already said that we will be concerned with the potential that are function of the relative distance between the particles. So potential is usually already given in terms of R. So we need to figure out a way to transform the kinetic energy of the particles from their absolute position to the kinetic energy in terms of the center of mass and the relative coordinates. So for that, let's start from this thing. Suppose the total kinetic energy is half m1 R1 dot square plus half m2 R2 dot square. R1 dot is the derivative of R1 with respect to time. And this R1 dot square is nothing but R1 dot. So this dot is the dot product between R1 and this is the dot product between R2. So from here, if you substitute this R1 and R2 in this equation and evaluate this dot product and evaluate this dot product and then rearrange the terms, you can see that after rearranging, you can write it like this. Capital R dot square and M1, M2, sorry, this is M1 plus M2 over M1 plus M2 R dot square. By the way, R is just R magnitude and capital R is just the magnitude of R vector. So now let's introduce another notation. Let's say capital M is the total mass of the two particles, and we know introduce this another term called reduced mass, mu, as the reduced mass of this system. And now we can write the kinetic energy as half m r dot square plus half mu r dot square. So it means that the kinetic energy of the two particles, so this had position vector r1 and this had position vector r2. So instead of thinking of the kinetic energy of this particle and kinetic energy of this particle, we can think like this: kinetic energy of the center of mass. So if you are very far away from these two particles, you can essentially imagine them to be together and located at the center of mass with total mass m. So there kinetic, if you look from far away, you can see that this system is as a whole is moving this way or that way or towards here. So that combined motion, or you can say the total translational motion, is encapsulated in this term. So this is the translation of the center of mass. So this is the kinetic energy which is present in the system because of the total movement of the system. And then this term is the kinetic energy of the relative motion. For example, if you imagine another system in which there is only single particle of mass mu, and it's neither this nor that. Okay, this mu is not the mass of m1 and nor it is the mass of m2. It's another hypothetical system with a particle mu at a distance r from some origin where this one particle is located. So this hypothetical particle of reduced mass mu is moving internally. So this term is representing the internal kinetic energy sort of. And if the system isn't going anywhere, it means the translational motion of the center of mass is 0. So r dot would be 0. So there wouldn't be any contribution coming from this. And if there is no relative motion, for example, the distance between them is fixed, which means that no contribution is coming from them, and then the only contribution, if any, would be from the joint motion or the total motion of the system. So we can express kinetic energy in terms of center of mass motion and the relative motion with respect to each other. And by the way, we can also write it like this because we can express kinetic energy in terms of momentum as well. So we can write it the same term like this. So you can divide by mu up and down and by m up and down, and then mu r dot is the relative momentum here, and pm is the relative momentum of the center of mass. So it means I can now express the kinetic energy in terms of the kinetic energy of center of mass and kinetic energy of the relative motion of the particles. Now we can see that this term only depend on variable r, and this term only depend on variable small r. So we just saw that if we have, Hamiltonian with a term that only depend on R and a term that only depend on small r, we can reduce this problem to two simpler problems. One problem for center of mass and one problem for the uh, relative motion. And since our Hamiltonian, let me explicitly write it. So for the two particle system in an external potential, this Hm would be nothing but Pm square 2m, but this will be P mu square 2 mu plus there would be a potential term, because potential only depends on small r. It doesn't depend on the absolute position. So there's no capital R term. So it means this is H mu or HR and this is Hm. So it means our final wave function is just a product of two wave function where, and the total energy is the sum of the center of mass energy and the relative energy, where this psi m satisfies this simpler equation and psi mu satisfies this simpler equation than the total equation, like this. This is a bit more complicated than this one because this only have kinetic term and this has both kinetic and potential term. But the total energy is the sum of the center of mass term and the relative motion term. And if you want to, get a rudimentary picture, if you imagine, a hydrogen atom, something like this. Okay, let's take the Bohr model. So suppose this hydrogen atom is in some tube and it is not stationary, but it's moving. So if it is moving, then even if in the ground state, it would have two energy components. One energy is because of its overall motion, which would be given by Em. And then there is an energy which is because of the internal interaction of electron and proton, that ground state energy of minus 13.6 electron volt is given by E mu. And if now this emits a photon, if it is a ground state, it can absorb a photon and it can, let's say, go up, or similarly, if it is somewhere up state and de-emits, and suppose by emitting a photon, it also stops. So that, energy of the photon would be the sum of this term and this term. It wouldn't only be this one, because we will have to worry about the total energy and not just the relative energy. Most of the time we are concerned with the relative energy because this is, trivial, but you always need to keep, this big picture in your mind, that this is only one part of the problem and the total problem is the center of mass plus the relative. Okay, so any questions? I think we can stop here. Oh, somebody sent me a message that class time is over. I'm sorry, I had in my mind that we are going to go to 5 p.m. today, but I see that class is only 75 minutes.